Event cameras are bio-inspired vision sensors that output pixel-level brightness changes instead of standard intensity frames. They offer notable benefits compared to standard cameras, including high dynamic range, minimal motion blur, and low latency. However, output of event cameras is a stream of asynchronous events, where each event encodes the pixel location and polarity of the intensity change. These event streams cannot be directly interpreted by the human visual system, and also they cannot be used by traditional computer vision algorithms. Therefore, output of event cameras require novel methods in order to use them with existing computer vision methods. One way to achieve this is reconstructing intensity images from event data. In this work, we propose HyperE2VID, a dynamic neural network architecture for event-based video reconstruction. Our approach extends existing static architectures by using Hypernetworks and dynamic convolutions to generate per-pixel adaptive filters guided by a context fusion module that combines information from event voxel grids and previously reconstructed intensity images. The dynamically generated parameters are also spatially varying such that there exists a separate convolutional kernel for each pixel, allowing them to adapt to different spatial locations as well as each input. This spatial adaptation enables the network to learn and use different filters for static and dynamic parts of the scene where events are generated at low and high rates, respectively. To avoid the high computational cost of generating per-pixel adaptive filters, we use two filter decomposition steps while generating per-pixel dynamic filters. First, we decompose filters into per-pixel filter atoms generated dynamically. Second, we further decompose each filter atom into prefixed multi-scale Fourier-Bessel bases. We guide the dynamic filter generation through a context that represents the current scene being observed. This context is obtained by fusing events and previously reconstructed images. These two modalities complement each other since intensity images capture static parts of the scene better, while events excel at dynamic parts. By fusing them, we obtain a context tensor that better represents both static and dynamic parts of the scene. We also employ a curriculum learning strategy to train the network more robustly, particularly in the early epochs of training when the reconstructed intensity images are far from optimal. This curriculum learning strategy allows the parameters of the hypernetworks to be learned more robustly, enabling the training process to converge to a better performing model. We show that this dynamic architecture can generate higher quality videos than previous state-of-the-art, while also reducing memory consumption and inference time. Quantitative results were obtained from evaluating the methods on sequences from ECD, HQF, and MVSEC datasets. We evaluate the methods using three full-reference evaluation metrics: mean squared error, structural similarity, and learned perceptual image patch similarity when high-quality, distortion-free ground truth frames are available. To assess image quality under challenging scenarios, such as low light and fast motion, where ground truth frames are of low quality, we use a no-reference metric, BRISC. Our method achieves state-of-the-art performance in terms of most metrics. On the ECD and MVSEC datasets, it outperforms the second-best method, ETNet, by a large margin. On the HQF dataset, it delivers results on par with or slightly better than existing approaches. In challenging scenarios involving fast camera motion or night driving, it obtains the best BRISC scores, surpassing the second-best method, E2VID. In our experiments, we also investigate the impact of specific design choices while keeping all other training and evaluation settings unchanged. Specifically, we investigate hypernetworks that use only event context, only image context, or both event and image context. We further examine the impact of using the curriculum learning strategy and convolutional context fusion. Our experiments reveal that leveraging both events and images as contextual information generally outperforms other design choices. When using both events and images, incorporating only the context fusion yields performance improvement on the MVSEC dataset. Conversely, incorporating only the curriculum learning strategy enhances performance on both the MVSEC and HQF datasets. Combining all these components results in our proposed model, which achieves the best scores on ECD, MVSEC, and HQF datasets, and second-best scores on fast and night datasets.